Hello, everybody. Mr. Johnson with you once again. It is Saturday, September 26th. President Trump is expected to nominate Amy Coney to the Supreme Court. Wildfires are still raging in California. Ruth Bader Ginsburg is the first woman and Jewish person to lie in state at the Capitol. Those are a couple of your top headlines from September 26th. All right, this is Lecture 9, Section 4.1. Writing and Balancing Chemical Equations. We're on page 164 of our ebook. Hope you're looking forward to another wild ride. I'm going to take you momentarily to the site of my soon-to-be infamy, a little place I call YouTube, to show you a couple videos of a couple of reactions that will hopefully get you excited. All right, so we're going to see a reaction here between cesium and water. It's a single replacement reaction we'll learn about in a bit. We'll be writing this one out, in fact, and looking at what the products of this reaction are and why we see what we see here. There's an acid-base indicator in there actually called phenolphthalein that is responding to the production of a base, cesium hydroxide, and that's what's making the color magenta, and we'll learn about the chemistry of that later. It's a highly exothermic reaction. Lots of energy is released from the bonds that form relative to the energy it took to break the bonds, and that's why we see the little explosion there. The next reaction we're going to see is between copper and iron sulfate. We'll write that one out later. Also a single replacement reaction associated with some cool color changes. Copper is replacing iron in solution. That reddish-brown color is indicative of solid copper being formed in solution. And as the copper ions are gaining electrons from iron, forming solid copper, the bluish-green color that was in the water, due to the presence of copper ions, is going away as the concentration of copper ions drops. All right, back to our ebook. Off we go for another lecture. So scroll down here to the bottom of the page, looking at this section that's highlighted. And what this is representing is what we will be learning about in this short lecture, which is how we go from word equations to formula equations. It's essentially an exercise in naming/formula writing. We're going to learn about phases, how we indicate phases, and as well how to balance equations. In theory, this is something that you might have covered in your first year chem class. Just want to make sure that everybody feels grounded in this before we do some trickier things with equations. So I flipped my page. I'm on 165 of the ebook, or 157 of the textbook. We'll go over this section here in a moment, but first I want to remind everybody that chemical reactions involve the breaking and or forming of bonds, meaning that there's always going to be one or new substances that are formed. The reactant or reactants will be different than the products. That's a hallmark of a chemical reaction. There are often some identifying features that, if we observe something taking place, tell us it's a chemical reaction. The absence of these doesn't mean it's not a chemical reaction, but typically a chemical reaction will be accompanied by one of these features. So if we see a noticeable absorption or release of heat, significant temperature change, that's probably a chemical reaction. If there's a color change, that's also probably a chemical reaction, because substances tend to have their own characteristic colors, and when new substances are formed, there could be color changes. Very oftentimes in a chemical reaction, a gas is produced. So if we see bubbles being made or gas production, that's likely a chemical reaction. And in reactions as well, precipitates are often formed. Those are solids that are formed in the presence of an aqueous environment in solution. And if that solid that's formed is insoluble in water, then it will precipitate out of reaction and form a precipitate. And we'll be looking at precipitates and double replacement reactions a little bit later. So the first skill we'll talk about in this lecture is balancing chemical equations. Just want to remind everybody that chemical equations have to adhere to the laws of nature, one being the law of conservation of matter or mass, meaning that however many atoms we begin with is the same number of atoms we must end with in a chemical reaction. And more specifically, however number of each type of atom we start with is the number of each type of atom we end up with. In chemical reactions, the types of atoms are not changed, matter is not created or destroyed, and mass is conserved. I flipped my page. I'm now on 166 of the ebook, And I'm looking at this equation here, this balanced equation, which is adhering to the law of conservation of matter, where the same number and types of atoms are present on both sides. We see this coefficient, this number out front in front of mercury 2 oxide, suggesting that there's 2 mercury oxide molecules that react for every mercury atom that's formed and for every oxygen molecule that's formed. Or we could say that for every 2 moles of mercury oxide, there's 2 moles of mercury formed and 1 mole of molecular oxygen. Oxygen, remember, is always O2. Whenever there's pure oxygen in a chemical reaction, it's always O2. When oxygen's in a compound, it may have a different subscript. But again, oxygen, molecular oxygen, is always O2. Coefficients always get distributed throughout the formula. So if there's a 2 in front of HGO, that means there's 2 mercury atoms and 2 oxygen atoms on the reactant side. And then there's 2 mercuries on the product side we see. And O2 suggests there's 2 oxygens in the end as well. So notice that the number of each type of atom is the same in the beginning and the end, a hallmark of a balanced chemical equation. All right, so I've flipped the page, 167 of the ebook, taking a peek at this quick check at the top of this page, and I encourage you to take a moment and, as it asks you to, circle the letter of the properly balanced equations. Take a moment, please, to do the quick check. Pause this video, come back when you're done, and see if you've circled the properly balanced equations. All right, so I found that only C wasn't balanced. A, B, D, and D were. Notice in C that we've got 2 hydrogens to begin with and 4 in the end. That alone tells us it's not balanced. Furthermore, you've got 2 oxygens in the end and just 1 to begin with. All right, so we're going to go down now to this section that says keeping your balance, helpful hints. These are really helpful when you balance equations. There's other ways to balance equations, but I find these to be the most helpful hints. I'm going to read these to you. First one says to find the most complex formula and begin by balancing atoms that appear in only one place on each side of the equation. It's the second half of that statement that matters the most. Begin by balancing atoms that appear in only one place on each side of the equation, or are in only one reactant and in only one product. Atoms that are in more than one reactant or more than one product are trickier to balance, and they tend to get balanced through the balancing of other atoms. And we'll model this for you in just a little bit. The second hint says to balance atoms that occur in elemental form last. So if you've just got sodium, Na, in an equation, wait to balance it until the end, because that's easy. You just put a single number in front, and all that affects is the sodium. Third tip, real helpful, is that if you see the same polyatomic ion on both sides, if there's nitrate on the left, NO3, and on the right, balance the entity nitrate as one thing. Instead of balancing N and O's, balance nitrates. And we'll model that as well in a moment. Fourth tip, if a coefficient has been placed in front of a molecule, finish balancing the other atoms in that molecule that were affected by the coefficient you placed in front of it next. So if you've got KNO3 and you put a coefficient in front of KNO3 to balance the ends, and that somehow disrupts the number of oxygens, then you'd go and balance oxygens. Meanwhile, maybe you want to balance NO3 as its own anyways. So, last one is if you're starting with a word equation and then you're balancing it, be sure you write the formulas correctly. And if you end up struggling to balance an equation that you've written from a word equation first, it's possible that you wrote some formulas wrong. So just be really careful when you're writing your formulas before you go to balance. So I'm going to flip the page, and then we'll balance a few of these together, and in so doing, talk about the use of these tips and how they come to play. I've actually flipped 2 pages. I'm on page 169 of the ebook now, and I'm going to do 2A with you here at the bottom of that page. All right, so I've written out the reaction here on my whiteboard. We've got aluminum. That subscript S is denoting solid. That's an abbreviation we use for when something's solid, reacting with sulfuric acid that is dissolved in water. Remember, all acids to function as such need to be dissolved in water. AQ is the abbreviation for aqueous, or dissolved in water, forming aluminum sulfate, also dissolved in water, and hydrogen gas. G is for gas. The one abbreviation or symbol we don't see here is L for liquid. If one of these were a liquid, we'd see L. I'm going to do this little charting method here, which helps keep track of the types of atoms. I've written aluminum down underneath the arrow because aluminum is present on both sides. I'm going to write hydrogen down because hydrogen is present on both sides. And then the polyatomic ion sulfate is also present on both sides. So instead of balancing S's and O's separately, I'm going to balance sulfate as its own entity. And that's one of those tips that you heard me just talk about. If a polyatomic ion is present on both sides, balance it as if it's an element. So now I'm going to, on the left and on the right, indicate how many of each atom or ion there is to begin with. There's 1 aluminum on the left, 2 aluminums on the right. There's 2 hydrogens on the left and 2 on the right. And there's 1 sulfate on the left and 3 on the right. So we've got aluminums out of balance and sulfates out of balance. If there's a choice between what to balance first, remember you want to weight on any element or ion that's in more than one substance on both sides. That's not the case for aluminum or sulfate. Aluminum's in just one reactant and just one product. So is sulfate in just one reactant and just one product. So neither of those fulfill that criteria. So we could balance either aluminum or sulfate first. I tend to go with metals first. They seem often to get to the end sooner. So I need 2 aluminums on the left, and I put a 2 there. But remember, one of the other hints was balance individual elements last. So that might have been a reason to wait on aluminum because it was all by itself. I still chose to do it first. All right, now I need to balance sulfates. There's 3 sulfates on the right, but only 1 on the left. So I use a coefficient. I put a 3 out front. I never change the formula of a substance. Once it's written correctly when I balance it, I only ever use coefficients. So 3 out front. That gives me 3 sulfates on the left. But it also adjusts the number of hydrogens. So now there's 3 times 2 hydrogens on the left. That became 6. And I need to balance it next, not only because it's the only element left, but remember, a hint earlier was if by balancing one atom or ion, like sulfate, it disrupts the number of another atom, in this case hydrogen, you'd want to balance it next. So I need 6 hydrogens on the right. I put a 3 in front, and there we go. So if this method works for you, feel free to use it. If you're able and want to do it in your head, that's fine. But when reactions get trickier to balance and there's lots of elements on both sides, this can be a helpful method to help you keep track of things. I'm going to do 2B with you now. If you feel like you're getting the hang of this and want to do this one on your own, feel free. You might consider listening to my explanation, though, because I'm going to reveal a couple of more of those hints or tips for you in this one. All right, in this one we've got solid magnesium nitride reacting with liquid water, forming solid magnesium hydroxide and gaseous ammonia. NH3 is ammonia. We've got 3 magnesiums on the left to begin with, 1 on the right, 2 nitrogens on the left, 1 on the right, hydrogens, 2 on the left, but it's in 2 substances on the right, so I've got to pay attention to that. I've got 2 from here and 3 from here, so that's 5, and then 1 oxygen on the left and 2 on the right. Looks like everything's out of balance. At this point I want to decide what to balance first, or more importantly, what to wait on until the end. That hint that we heard earlier, which is that you want to wait on any element that is in more than one substance on any side of the reaction, you should wait on until the end. And that's true for hydrogen only. Hydrogen's in just one reactant, but it's in 2 products. Elements that are in more than one substance on one side of the reaction, you ought to wait on. So I'm going to put a little X here to say, hold off on hydrogen, do it at the very end, or maybe it will get balanced by balancing other atoms. So I now have a choice between magnesium, nitrogen, and oxygen. I tend to go with the metal first, like I mentioned last time. So I need to put a 3 in front of magnesium hydroxide to get magnesiums to 3. That altered oxygens, which were 2, but now 3 times 2 is 6. Same thing for hydrogen. 3 times 2 for hydrogen is 6, plus these 3 were 9. Another hint you heard is to next balance an element that was just altered by having balanced a prior element, and that's true for hydrogen and oxygen. So I'd balance one of these next, but having decided already to wait on hydrogen until the end, I'll go with oxygen. 6 on the right, 1 on the left, put a 6 in front, and that also altered hydrogens to 12, which I would balance next, except again, I've chosen to wait on hydrogen until the end. So I'm going to go with nitrogen now. And with 2 on the left and only 1 on the right, I'll put a 2 in front of NH3 to balance nitrogens. And that takes hydrogens on the right up to 2 times 3 is 6, plus 3 times 2 is another 6. 6 and 6 is 12, and we are done. And lo and behold, hydrogen did balance itself, or got balanced through the balancing of other atoms. You don't need to do this method if you can do it in your head. You don't have to follow the hints. You can do guess and check or whatever works for you. But the hints do end up being really helpful, particularly when equations are tricky to balance. And this one is sort of an intermediate one, I would argue. All right, I'm going to flip my page, 170 of the ebook, and do 2 with you. This is a word equation. What we'll first do is convert this word equation into a formula equation. It's an exercise in naming, formula writing. We'll include those abbreviations as subscripts for the phases, and then we'll go and balance it. I'm going to go to my whiteboard, and I'll see you there in a moment. Oh, there I am. Amazing. Click, and here we go. Aqueous solutions of ammonium phosphide and lead-2 bromate react to give a precipitate of lead-2 phosphide and aqueous ammonium bromate. All right, well, ammonium I know is NH4 1+. Phosphide is P3-. When I crisscross, I get NH4 sub 3P. And it is aqueous, so I go AQ. All right, 1 down. Now I've got lead-2 bromate. That Roman numeral 2 is telling me lead is a 2+. Bromate is BrO3 1-. And when I crisscross, I get PB in parentheses BrO3 sub 2. It's also aqueous, AQ. Reacts to give a precipitate of. That word precipitate means a solid formed in the presence of an aqueous environment. So it's going to be solid. Lead-2 phosphide. Lead's still a 2+. Phosphide's still a 3-. So we're going to get PB3, P2, solid, and aqueous ammonium bromate. Ammonium is NH4+. Bromate is BrO3 1-. We know that already, so we're just going to get NH4 BrO3AQ. All right, so there's my formula equation. We're going to balance this now, but I'm not going to do the keeping track of atoms method. I'm going to model what it would look like if you chose not to do that. Looks like we got 1 lead on the left, 3 on the right, so lead's out of balance. Looks like we got 2 bromates on the left, 1 on the right, bromate's out of balance. Ammonium, 3 left, 1 right, ammonium's out of balance. And phosphorus, 1 left, 2 right, phosphorus out of balance. They're all out of balance. No substance or species is in more than one substance on either side of the equation. So I could really go with any of these. And again, I tend to go with the metal first. I'm going to go with lead first. 3 leads on the right, 1 on the left. Put a 3 there. And that changes bromates to what was 2. 3 times 2 is now 6. There's now 6 bromates on the left. I need 6 on the right. I always forget to leave space before my formula, so I'm going to put a 6 in front of ammonium bromate, balancing my bromates. So at this point, lead and bromate are balanced. But this 6 altered ammonium, so I now have 6 ammoniums on the left, and I had only 6 ammoniums on the right. I had only 3 on the left. So I'm going to balance ammoniums next, because they were altered by balancing bromates. Put a 2 there, and that balances ammoniums, and it gives me 2 phosphorus on the left, which are equal to the 2 phosphorus that were on the right to begin with. And that, folks, is balanced. Furthermore, that is a wrap on 4.1. Good luck balancing. Enjoy yourselves. Have a great afternoon, or morning, or evening, depending on what time of day it is.